So, hello and welcome to lesson 2 of our study of differential equations 1. So, in this lesson, we are going to learn how to classify differential equations. So, Bodo Randolph, a final year student of mathematics, KNUST. Please don't forget to like the video and subscribe to the channel for more videos, okay? So, how do we classify differential equations? For instance, when we have human beings, okay, one way we can classify human beings is to use gender. So you can say, okay, so males go here, females go here. We can also use maybe color. Those who are white go here, those who are black go here. We can use maybe your nationality. If you're a Ghanaian, go here. If you're a British, go here. If you're a Togolese, go here. So we can have different ways of classifying things. Even when it comes to things from our basic knowledge from basic school, we said we could classify things into what living things and non-living things. So when it comes to differential equations too, we can classify them into various classes based on some rules, okay? So we do the classification of differential equations based on four main things. So based on the type, the order, the degree, and linearity, okay? And sometimes we do add homogeneity. So we are going to learn how to classify differential equations using these five things: the type, the order, the degree, the homogeneity, and the linearity, okay? And it's not something difficult at all, so please pay attention and follow me with your heart. And yes, by the end of the lecture, you understand. So let's take a look at the first one. That's classification by type, okay? So when it comes to classifying differential equations based on the type, we have two of them. We can have an ordinary differential equation or a partial differential equation, okay? So we can have an ODE or a PDE. So what's an ordinary differential equation? ODE. So an ordinary differential equation is one containing ordinary derivatives of one or more unknown functions with respect to a single independent variable, okay? So you know ordinary derivatives, the y, the x, the s, the t. So when you have any of these in our differential equations and it contains just one independent variable, right? So that means if you are differentiating with respect to x, it will be with respect to x throughout. If it is t, it will be t throughout because we have just one single independent variable. Then that differential equation will be an ordinary differential equation. So let's take a look at some examples. You see, you can see dy dx equals 3x squared. It contains ordinary derivatives, right? And another way you can also know that is it has just one independent variable. You can see here the independent variable is just x. So here it contains just ordinary derivatives. That's example 2. And we have just one independent variable. And the same applies to example 3. Contains ordinary derivatives. We have just one independent variable, that is y. So that's what an ordinary differential equation is. You see, it's very simple. Okay. And in our study of differential equations, that's what we'll be focusing on. Later on in third year, you study partial differential equations. So, what's a partial differential equation? For the purpose of learning a classification by type, you have to know what that is now. But you learn that into details later on, okay? So a partial differential equation is one involving partial derivatives of one or more dependent variables with respect to one or more independent variables, okay? So you can remember from your mass methods class that you're learning partial derivatives. So I hope you know how to write partial derivatives, okay? So if your differential equation contains partial derivatives, then that differential equation will be a partial differential equation. And most of the times, with that one, you can have one or more um, independent variable. Most of the time, two or more. Okay, mostly. So examples are del v del t equals h squared, everything here. So you can see here, for instance, it contains partial derivatives. So that should tell you it's a PD. Aside that, the independent variables are t, x, y. You can see more than one. Then here too, it contains partial derivatives. So that should give you a clue that it is a partial differential equation. And you could see that the independent variables here, x and y, more than one, right? Okay, so that's how we classify differential equations based on type. We can have either an ordinary differential equation or a partial differential equation. And we just learned how to know which of them is this and which of them is that. So ordinary contains ordinary derivatives. You can see that it will always have just one independent variable. Then the partial derivatives contain the partial differential equation contains partial derivatives. We have more independent variables in that one. Okay. So let's go to the second classification. We are going to learn classification by order. So what is the order? What do you mean by order of a differential equation? So the order of a differential equation depends on the order of the derivatives, okay? And it is the number of the highest occurring derivative, or it is the order of the highest order derivative operating in the equation. Did you understand these words put together to form this statement? If not, don't worry, okay? We will explain it mathematically with examples. So let's take some examples. So look at the first question, question 1 here. So you see we have d squared y dx squared plus 2b times dy dx plus y equals 0. So you can see that we have two derivatives here, this and that. So we ask ourselves, out of these two derivatives that we have, which of them contains the highest order? You can see that this one has an order of 1, but this one has an order of 2. So that means this differential equation will have an order of 2. And most of the time when it has an order of 2, we call it a second order differential equation. But here I said a second order ordinary differential equation because you can see it contains only ordinary derivatives, and so it's an ordinary differential equation. So I hope you see how we get the order of a differential equation. So example 2. So you can see that we have this derivative here and that here. Okay, but you can see that this one has an order of 2 and this one has an order of 4. So the order of this differential equation will correspond to this. So it will have an order of 4. Please don't try and multiply this 3. Don't multiply it here, okay? This 3 also has another importance. We can also classify a differential equation based on that, and that's what we call the degree. And we will learn that one after learning the classification by order. Okay, so never try to multiply it and say that it is 12 or something like that. No. So this one has an order of 4. Then when it comes to this third example, you can see that we have only 1 here. It has an order of 1. So this is a differential equation of order 1. So we call it first order. Okay, so that's it. That's how we classify differential equation based on order. Very simple, right? So let's go to the classification by degree. So what's the degree of a differential equation? So the degree of a differential equation is the power of the highest derivative term. Okay, all right. So let's solve it. Let's look at examples to explain them. So you can see I have a differential equation here. How many derivatives do I have? These two, right? And you can see that this one here has an order of 1. Do you know that? Yes, we just discussed it, so you should know that. Then this one has an order of 3. You can see that. So out of the two derivatives that we have, you ask yourself, which of them has the higher derivatives, because we are comparing two things here, so higher, right? Okay, so you can see that this one has the higher order, the higher order. All right, and to which power is it raised to? It is raised to what? Power 2. So that means that this particular differential equation will have a degree of 2. Okay, so don't say it is 3. That's not how we do it. We first look at the one which has the highest order. Then the power to which it is raised become what? The degree. So for instance, I was telling you, in this example, for instance, since the order was 4, if we're looking for the degree, it will be of degree what? 3. I think that one is even here. Yes. So that's what we just explained. So you see this one here, this one has the highest order, and this is raised to the power what? 3. So the differential equation will be of degree 3. So let me write a third example. So maybe dy dx equals 3s squared. So this one, you can see that it has just one derivative here, right? Which is dy dx, and it is of order what? 1. And it's also raised to the power what? 1. So that means here it will be of degree 1, right? Okay, so that's how we classify differential equations based on the degree. Now let's classify it based on homogeneity, whether it is homogeneous or non-homogeneous, and it's the simplest you can ever have. Okay, all right. So let's consider an nth order ordinary differential equation of the form a n y, the derivative is n plus whatever you can see here. Okay, so when this f of x here is 0, that means that our differential equation will be homogeneous. If it is non-zero, then that means our differential equation is non-homogeneous. Okay, so let's take example. So you can see that here we have all our derivatives here. By the right hand side, we have something there, 5x. So it makes this non-homogeneous. Okay, so the first one is non-homogeneous. Then the second one, 2 is homogeneous because we have all the derivatives and the y here, right, and the x here, because the x is the dependent variable, but the right hand side is what? 0. So it makes it a homogeneous differential equation. Maybe let me write a third example to make sure you really understand it. So let's say we have dy dx minus 3s squared is equal to 0. So is this homogeneous or non-homogeneous? So you can pause the video, think about it, right? So in 3, 2, 1, let's answer. So if you said this is homogeneous, then you are wrong. It is homogeneous. Do you know why? Because this here can be written as dy dx equals 3s squared. And you can see that it doesn't contain the dependent variable here. So it makes this the non-homogeneous term. So this here is non-homogeneous. But we have something of this form. Dy dx equals maybe 3s squared y. This here is homogeneous because of the y here, right? So this one can be written dy dx minus 3s squared y equals 0. And that is homogeneous. So if you still don't really get the homogeneous and the rest, try to solve more questions from different sides and you understand. Okay, it's very simple. That's the simplest you can have. So now let's go to the last thing we are going to be doing in this video. Classification by linearity. So this is when we determine whether our differential equation is linear or non-linear. Okay, so there are some conditions, 3 conditions, which has to be satisfied for a differential equation to be linear. If any of them is violated, then our differential equation will be non-linear. Okay, so it is those 3 rules that you have to learn and understand them. So These are the three conditions or rules. So the first one is that the dependent variable, and by now you should know what the dependent variable is and how to get that from your differential equation. So the dependent variable and all its derivatives occur only in the first degree. By now, you should know what the degree of a differential equation is and how to find it. So you see how the thing is. The thing is systematic. That's the reason why we learn this before we learn that and these things. So if you don't really understand some portion, moving forward, you are going to have problems. Okay, so make sure you understand lesson 1 before you move to lesson 2. You understand lesson 2 before you move to lesson 3, because it's like that's how it's supposed to be. If not, it's very difficult for you to understand the subsequent ones if you don't understand the previous ones. Okay, so the first condition states that the dependent variable and all its derivatives occur only in the first degree. The second one says that no product of the dependent variable, say y, and or any of its derivatives was present. So we shouldn't have anything like, for instance, if y is the dependent variable, we shouldn't have anything like y squared, y cubed. We shouldn't have anything like y times dy dx. Maybe y times d squared y dx squared. Things of that form. Okay. So that's for the second one. And with the third one says that no transcendental function. You know what a transcendental function are? The trigonometry, so like sine, cos, tan, arc sine, and the rest. Then or logarithmic or exponential of the derivative variable and all of the dependent variable and all its derivatives what okay. So we shouldn't have anything like, maybe if y is the dependent variable, we shouldn't have anything like cos y, e y, like ln y, maybe ln dy dx. These things shouldn't happen. If they happen, then our differential equation will be non-linear. Okay, so let's take some examples here. So you're supposed to classify the following as linear or non-linear. Okay, so let's solve them together. You see, it's very simple. So with the first one, I am saying it is linear. You know why? Because you can see that we only this is the only derivative we have here, and it's of degree 1. So the first rule is satisfied. The second one, so we don't have any product of all the dependent variable and itself or its derivative. And also the dependent variable y is not in any transcendental function. So it makes this one what? With the second one, you see the degree here is 2. So this alone makes it what? Non-linear. Because at least one of the rules or conditions is violated. Here too, it is non-linear. Do you know why? Because the dependent variable is y, and we are having y squared, which is y times y. So this is also non-linear. So the third one is also non-linear. Do you know why? Because the dependent variable y is appearing in the transcendental function. So you see, I intentionally picked examples to explain all the points to you. Okay, so you have to understand the conditions and what they mean, and it's very simple for you to use them to identify whether a differential equation is linear or non-linear. Okay, then let's look at the last example. So in the last example, you can see that this is also non-linear. Can you tell me why? Pause the video and please think about it. After some 30 seconds, I'll tell you the answer, but pause the video and think about it. Okay, so in 3, 2, 1. Alright, so the reason why it is non-linear is because of this here. You see, the dependent variable is y, and we have a product of the dependent variable and what? Its derivative. So this makes it non-linear. Okay, so in this video, we learned how to classify differential equations, and we took our time to digest them, right? So I hope you really understand it. So don't forget to like the video and subscribe to the channel for more videos. So in our next video, that's lesson 3, we will talk about the solution of a differential equation. So what's a solution to a differential equation? How do you verify that a particular function is a solution to a differential equation. So see you in the next video. Thank you.